All right, everybody, welcome back. So today's lecture is going to be on interactions. So we've discussed interactions a little bit. This is the idea of putting a product term in as a predictor into a linear model. But I sort of gloss over them kind of quickly in the context of multiple linear regression. And so in this lecture, we're going to look at them in more detail. When should we add them? Uh, and yeah, this is just basically the big idea. Why are interactions useful, and what's some intuition we can provide ourselves for when we should include interactions. References in the course text, if you'd like to find some more information. Okay, so as I said, so we talked about in the multiple linear regression lecture that including interaction terms in your model can be one way to improve it. And the included, what does an interaction term mean? This is an example of language vocabulary that is not particularly descriptive. When we say interaction term, we mean the product, right? But there's multiple ways to have two variables interact. But what we mean by interaction is that in sort of a statistical sense, or in this particular setting, we mean their product. And this is the notation that we've seen. We've seen that we can use the colon between two predictors to generate an interaction term. This is just a product term. So this is when building a linear model. You can include the colon as a way to take the product of two predictors. This is the same linear model as if we had used the identity. So that just means the identity just tells R. Don't use your funky formula syntax. Just include the product in the model without treating this product term as formula syntax. If you actually use the product, it will generate factor crossings. So what factor crossings are, and again, we talked about this in the multiple linear regression lecture, so this is a little bit of review, but you take each term individually and then their interaction term. And so using this formula, so generating a linear model predicting y from this factor crossing is the same as building a model where you use one predictor, the other predictor, and their product term. Okay. And the caret sign, the caret symbol will generate higher order factor crossings. And so what this does is this takes a factor crossing between x1 and x2. And so this basically takes the pairwise factor crossings. So when you have a pairwise factor crossing, you generate a factor crossing for x1 and x2, a factor crossing for x2 and x1. These are the same factor crossing. And then x2 and x2 and x1, x1. These are just x1 and x2 individually. So you end up with the following linear model. All right, so that's just recalling the R syntax. Last thing is that if you use the poly function, you can generate polynomial terms. These polynomial terms include crossings. So if you say generate a d-degree polynomial, it will include, for example, poly x1, x2, 2 will generate x1 squared plus x1, x2 plus plus x1, x2 subscript not a superscript plus x2 squared plus x1 plus x2, right? And so what this does, right, is this is giving you the factor crossing. So I'm mentioning the poly here because it will generate the polynomials. This is second degree term, one from x and one from x1 and one from x2. So I mentioned this. You can define interaction sort of in an English sense a lot of different ways. You could have an interaction between two variables could be 1 over x1 plus x2 is the interaction between x1 and x2. You could take something funky like sines and cosines or their ratio, or right, some in terms of an English description, and interactions just means that there's two things going on at once, right? An x1 input and an x2 input. So why is the canonical interaction term a product? Okay, So I think there's two reasons. The first one, I call it the ancestors. So this comes from our Truth About Linear Regression text. It has been handed down to us, and we don't have any strong reason to deviate from that tradition, right? So it's not a super satisfying answer, but sometimes it's just the way it is. The second reason is actually Taylor's theorem. So if you remember Taylor's theorem from your calculus classes, what it gives is if you have a smooth multivariate function, you can actually form a Taylor expansion by, so you want to you have a inputs x1 and x2, you want to form a Taylor expansion around some point x1, x2, and you can actually do so by taking derivatives times first order terms and their products. Okay, so this is one. So this is a one expansion. This is an expansion plus some higher order terms here. So what this is doing is saying you have your zeroth order terms, you have your first order terms, your second order terms, and your first order term, another first order term, and a second order term, which is the mixed partial derivatives of your function g. So Taylor's expansion actually shows that if you have a smooth multivariate function, you can perform this Taylor expansion. So again, these higher order terms are in general important, and you can only sort of they only become very small when the point you're expanding around is close to the input point that you care about. But what this shows is that you can perform this expansion, which looks very much like a factor crossing. So you have a zeroth order term, right? When you have a fixed point x1, x2, this just becomes your beta naught. This is a constant, and then this is a constant piece, right? So this times this one can be incorporated into your beta naught when you multiply them out. This piece becomes a slope, and this is your predictor, slope, predictor, and then constant piece again, right? And then this here gives you the interaction term, right? If you FOILed this out, you would get a little bit contributing to your x1, a little bit contributing to your x2, a little bit contributing to your constant, and then you would have the pairwise product of x1 and x2, and this is your interaction term. So Taylor's theorem gives some loose justification for why an interaction term of the product is natural, because as you proceed to do this expansion, it just pops out naturally, right? So your higher order terms would have then quadratics in x1 and quadratics in x2. So that's so this is the two reasons why I see, or why in my opinion, the interaction term, the canonical interaction term is fairly natural, right? One just being it's handed to us, the other being that Taylor's theorem says that it's somewhat natural. Okay, so so if we have this expansion, okay, sorry, this is what I just did on the previous page. So sort of expanding and collecting terms. This is the canonical form of factor crossing. So I will skip through that. Okay, so when do we actually use interactions? Okay, so the intuition behind interactions is that if the relationship between x and y changes, so let's say we fix x1, right? If the relationship between x1 and y depends on knowledge about x2, we might want to include an interaction term, okay? And so this is sort of the intuition that I'm looking for. And sometimes this is difficult because sometimes you just have to try it because you might not know based on context, right? If it's a domain that you don't have a lot of subject matter expertise on, sometimes you can just try an interaction and see. But if you have a lot of predictors, you have a lot of interactions. But this is the question that I'm asking myself, or I'm asking a subject matter expert that I'm working with, is okay, I'm trying to build a model, trying to develop some intuition for what predictors are going to be important. If I include information about x2, does that change the relationship between x1 and y1? Okay. So here's a couple of examples. The first example is on the body fat data set. So the body fat data set is a data set where we have a bunch of measurements. I think there's 250 people in this data set. They're all men. and we have various predictions, various measurements of like waist circumference, bicep chest circumference, wrist circumference, knee circumference, all these different measurements, along with percent body fat. And the idea is we want to predict percent body fat from these different measurements. And so in this sense, so in this context, so a person with a large chest and a narrow waist, right, might be expected to have lower body fat than somebody who just had a narrow waist, right? The idea being that if you have a large chest and a narrow waist, I don't know, maybe you're ripped, right? Sort of you have this triangle-shaped chest, and you just told me somebody had a narrow waist. Well, they could have a narrow waist because they're in shape, or because they're sort of just naturally run a little thinner, but they're not necessarily in good shape, right? So in that sense, I'm sort of thinking, okay, well, I could try an interaction term, because large chest paired with narrow waist tells me something different, potentially different than just a narrow waist. Okay, so intuition says I should try an interaction term, and I'll try this in R and test this and see if it's useful in just a moment. But let me go first to a second example. The second example is this insurance data set, which I have from this Machine Learning with R textbook. And so the idea is you want to predict insurance charges from clients' information. So you're maybe an employee at a health insurance firm, and you want to know how much premiums you should be charging different individuals based on their attributes. Okay, so in the insurance data set, we have one variable is smoking, whether or not the individual smokes, and we have another variable which is BMI, right? So in general, low BMI probably be associated with a healthier person, right? But a person who smokes, smoking generally is known to help people stay a little bit thinner. So a person who smokes and has low BMI, I wouldn't say that they're healthy. Maybe they're just thin because they're smokers, right? They might not have healthy lifestyles. From the perspective of an insurance firm, I might say those people are high risk, whereas in general, if you told me that somebody's low BMI, it would put them into a lower risk category, right? So in that sense, knowing that a person has low BMI, the relationship between the variable that I want to predict, that is the insurance charges, has a different relationship when I know that the person smokes, right? And so my intuition says try an interaction term here, right? Because the relationship between low BMI is changing given the information that the person smokes. Okay? So these are just two examples of how I asked that question. Is an interaction term useful here? Okay, so let's do this in R. So here I have both of the data sets, and I'll post this code so you can follow along with it, but this is the body fat data set, this is the insurance data set. I will load them both up. We've seen this function before, so this function I had in the previous lecture on categorical predictors. This is the function that will produce many train test splits and reduce the testing RMSEs for reps number of train test splits. And so what I'm going to do here, I'm going to take my test RMSEs. I'm going to predict percent body fat from waist and chest, and here I'm going to do the factor crossing. All right, so the only difference between these two is one of them includes an interaction term and one of them does not. Okay, so if I do my test RMSEs, so here I have my mean and my standard deviation of the 10 test RMSEs, and here I have the mean and my standard deviation of the 10 RMSEs, and here I see that my sample mean for test RMSEs has gone up. Right, adding the interaction term actually gave me a worse model from the perspective of the sample mean of these 10 testing RMSEs. Okay, so it's not helpful. Okay, this happens. So I was talking through my interpretation and why I thought that an interaction term might be useful. It didn't bear out in the data. That just happens, right? It doesn't mean I'm a bad data analyst, and if you do this, it doesn't mean you're a bad data analyst. But sort of thinking through the problem, trying some things, didn't work out. Okay. Performing the same for here I have the model with smoker and BMI as individual predictors, and here I have the factor crossing where I include the interaction. and doing the test RMSEs, we see a dramatic drop, right, when I include the smoker when I include the interaction term. So here we see that indeed the interaction term was useful. So the smoking interaction, and you could probably tell that maybe, well, it's a little easier for me to explain that one, which is one hint that it's probably more intuitive for people to understand, might hold through the data more. But what we see is that including the interaction term, so that is it helps us in terms of our model, and that is the relationship between smoking, or between BMI and charges to the insurance firm is different depending on whether or not the individual is a smoker. Okay, so let's jump back to the slides. So we see punchline from the R examples. The second example, our intuition, sort of the test RMSEs confirm our intuition, but the first term we didn't see it working out. Let's talk a little bit about how to interpret interaction terms. So in the insurance example, which is the one that was successful in terms of the interaction term benefits us, we had the following predictors, right? One for each, and then the interaction term. So remember that this X smoke or smoker, here I've dropped the R, but I'm referring to the same variable. This is a binary variable. 1 if the individual smokes, 0 if the individual does not smoke. Okay? And so, well, I'm assuming here that non-smoker is a reference category, so that is, as I've just described, X0 is the non-smoker. So the interaction term is here, right? It's only non-zero when the individual is a smoker, because this is binary times some predictor. Okay? So what's happening is we are this predictor in this factor crossing here. This BMI really this whole term is only being added in when the person smokes, because otherwise this is 0, right? So and when this does happen, when the person is a smoker, then the coefficient of XBMI is adjusted, right? Because what's happening is we have a coefficient attached to this term. When smoke is 1, we adjust the BMI coefficient by whatever the coefficient of the interaction term is. Okay? And so what's happening here, just writing this out, we have betas attached to each of the predictors, right, including the interaction term. What's happening is that if smoker is true, right, the prediction is we have a intercept, we have an adjustment. This is the contrast for the smoker, right? That is the person is a smoker, and then we have the slope for the BMI term is the slope of XBMI plus the slope of the interaction term, because smoker is equal to 1. Okay. Whereas if this person is not a smoker, then we just have this. We have the intercept plus the term for the BMI predictor, because smoker is 0, and so both of these terms cancel. Okay? So what's useful here is actually including the interaction term. We see that the binary variable has an adjustment on the intercept, and also on the slope of the BMI term. This beta 3 is basically an adjustment on the slope of the BMI term with the knowledge that the individual is a smoker. Okay, so a little bit of just convention. This is that it's bad form to use an interaction term in a model without using the original predictors used to generate it. Okay, so that is the interaction term is the product, and the original predictors are just there. So for example, x1 and x2, the interaction term is x1 times x2. So it's bad form to use the product term without the original terms, right? So what this is suggesting is use factor crossings over product terms. Okay, so this is factor crossing instead of just their product, right? Because factor crossing will include the original predictors by default, whereas this product term will not. Okay, Why is that? Why is this convention? Why is this important? Well, it actually mostly has to do with interpretation. So if we had a model, right, which had only an interaction term, well, if we rescaled the units of the predictors, right? So for example, we adjusted from, this is something that happens when you convert from Celsius to Fahrenheit, right? You perform a conversion like this, right? This is this affine conversion, adding a slope or adding an intercept multiplying by a slope is very common. Changing units. If you change the units of the predictors like this, you actually change the form of the model, because when you do this ax plus b, the b terms you can plug them in here and expand. You end up with something where you have coefficients for x1 terms or x1 terms, x2 terms, and their interaction. And so this is counterintuitive. Because we want the general form of our model to be robust to these rescaling the units of the predictors. If we rescale the units of the predictors in this affine way, we want to be able to change to keep the original form of the model, right? And this is why we prefer to always use the factor crossing instead of the interaction term, is so that the form of the model stays the same, even if we rescale the units, for example, converting from inches to feet or something like this. Okay, so use factor crossings instead of interaction terms. Sometimes useful to have this syntax in case you want to do something unique, but in general, these are better. The factor crossing is better form of a model. Okay, so that's all I have for this lecture, and I will see everybody next time.